Welcome to the NT podcast, Science and Theology podcast. My name is Nemanja Jurišić, and today we are delighted to have a guest like Professor John Walton, a chemist from St. Andrews University. Dr. Walton, thank you for coming and welcome.
Hello, Nemanja. Thank you for inviting me. It's a pleasure to be here on your channel.
Thank you so much. Today's topic is how did life originate? So let me just read your biography for those who don't know maybe. Dr. John C. Walton joined the faculty of Dundee University in 1967 and moved to St. Andrews University in 1970, rising to full professor in 1997 and becoming research professor in 2007. He has worked on the application of physical organic methods to organic mechanisms and is known for EPR spectroscopic studies of many kinds of radicals. So there is a lot of more. I don't know even what that means. So I'm not a chemistry guy. So I just want to say that Dr. Walton published over 300 articles, which is too much. So, Dr. Walton, do you want to say at the beginning something about your projects, research, and other stuff?
Well, I'm now kind of retired in that I'm not doing very much chemistry anymore, although I'm still associated with the staff at St. Andrews University. So I'm mainly working on books now, mainly books in the area of science and faith. Do you want to hear about those, or do you want to hear about my former chemistry work?
Yes, go on first, and whatever you want.
I often give talks on science and faith, and I decided that I'd write some books on the subject. And the first one that I published was called Compact Time. I can show you what it's like if you like. That's what the book is, and it really brings together a lot of information showing that the world that we live in is thousands of years old rather than billions of years old. And in particular, it focuses on radiocarbon dating of dinosaur fossils, of coal seams, how that works, and then also the soft tissues that have been discovered in dinosaur fossils, things like blood vessels and DNA and proteins. So that's one book that I wrote. Now, another one was that people like stories. You know, they're not so very fond of scholarly books. They tend to like stories. And so I thought I would incorporate some of those ideas into an exciting story at the same time. So it's a story about a girl at a university. She's a Christian and she's attending a paleontology course, and she puts in creationist ideas into this paleontology course and makes herself very unpopular as a result. So she has an exciting time trying to remain vocal when people are trying to silence her as a creationist at this course. She meets up with an atheist young man, and there's a romance is kind of developing during the book as well. So that's another interesting aspect to it. It's called Silencing Outspoken Ambrosini. It's available on Amazon. My other book's available on Amazon as well. Now I'm in process of publishing another book called Justice for Genesis, which deals with a lot of the scientific, I won't say problems exactly, but can one reconcile a lot of the things that you see in Genesis? Creation, rapid creation, the language in Genesis, the archaeology of Genesis. Does God exist? Can miracles happen? All these kinds of things that are dealt with in that book. I'm hoping that will come out in a few months' time. It'll be called Justice for Genesis. And then right at the moment, I'm writing another novel, which it's not a sequel to the first one exactly, although some of the characters do reappear. But again, it will be dealing with some science and faith issues and bringing them to the notice of readers in the context of an interesting and at times quite exciting story. So that's really the projects that I'm working on at the moment.
All right, so that's really amazing and interesting. So, yeah, can we start with the first question? I have only four, but we can chat little if necessary. So, how likely is that the life originated in a completely naturalistic way? There are three hypotheses how life originates. So, the first one is hydrothermal vents, second, tidal pools, and of course, panspermia hypothesis. So, could you comment each of them of those theories and say, are they a good explanation for life's origin?
Yes, it's a very interesting question and got lots of ramifications. Defining exactly what life is quite difficult. It's well known that it's quite difficult, but almost everybody agrees that to be living, uh, an organism must be able to reproduce itself and it must have metabolism. There are other things as well, but those two are sort of key cornerstone things. And the smallest known free living organism is called Mycoplasma genitalium. It's a little tiny organism. It lives in our genital tracts and it has DNA with 500,000 nucleotides in it. Now, a nucleotide is a substance composed of sugar, phosphorus, phosphate, and a base, a heterocyclic base. So they're often called bases or nucleotides, and these are the units that make up DNA polymers, DNA strands. Now, of course, Mycoplasma genitalium, the smallest known living thing, has enzymes and ribosomes and a cell wall and a membrane, cytoplasm and plasmids all there as well. This is the smallest thing that's known. There's another one called Carcinella rudi. It has 160,000 bases, nucleotides, but it needs a host to reproduce. It can't reproduce on its own. So most people don't claim it's the smallest living thing. Now, suppose for a minute that there's some kind of primordial soup where these nucleotide bases can couple up in a random chemical process to form DNA. They have to couple in the right order or the DNA won't be biologically active. Suppose the DNA were only 3 bases long, so there's just 3 coupled together. Well, just take 3 of them, you can get 6 possible DNA chains from coupling those 3. And if the DNA were 10 bases long, already the number of possibilities is over a million different DNA strands from just 10 of the nucleotides or bases. And if there were 77 bases, which is what you get, for example, in a transfer RNA, then the number of possibilities is 10 to the power 46. Now that's as 1 with 46 zeros on it. So that's an astronomically large number of possible DNA strands just for 77 bases. You know, the number of stars in the visible universe is 10 to the power 24. That's 1 with 24 zeros after it. So how could just the few DNA or RNA chains having the right properties for the start of replication happen to have appeared by a random process, searching amongst all those zillions of possibilities? You know, we're not talking about a needle in a haystack here. It's essentially infinitely more difficult than that. For random chemical origin of life, we're not talking about climbing Mount Improbable. Chemical evolution is stuck at the bottom of Mount Impossible. There's another way of looking at it, and that's the chemical space concept. I don't know if a lot of people are not familiar with chemical space. It's a virtual imaginary domain that's populated by all possible molecules. That's all the molecules that could possibly be made from combining in all possible ways all the known elements that are in the periodic table. Now, research has shown that if you just take a small set of 30 atoms, then the sum total of different molecules that could be made by combining them in all different ways is about 10 to the power 24. That's 10 followed by 24 zeros. So that's roughly the same as the number of stars in the known universe, which is a big number, as I think everybody will agree. Now, of course, the total population of chemical space from larger numbers of atoms is multiple orders of magnitude greater than that. And again, published estimates put the population of drug-like chemical space at about 10 to the power 60 molecules. That's 1 followed by 60 zeros. So that's an awful lot of molecules. So in the incredibly vast popular chemical space, finding new antibiotics is very difficult. And that's why it's such a severe problem and why the growing resistance to drugs is such a serious thing. Now, a naturalist, a materialist account of the origin of life has to explain how the comparatively small number of functional biomolecules, that's DNA or proteins or so on, that would be needed for the start of life, how could they be both identified and obtained by undirected means from the stupendous number of possible ones in chemical space? There simply isn't enough time. Meaningful explanation of this ocean of compounds is impossible, even computationally. It can be shown that it's impossible computationally in the supposed lifetime of planet Earth. And this is gradually dawning on the scientific community. You know, even if searching was carried out for 4 billion years by random processes operating at the maximum rate of chemical reactions, only an infinitesimally small fraction of chemical space could be explored. The Chemical Abstracts Registry, the CAS registry, that holds information on virtually every chemical substance made by the world's total scientific community from every country. Now, it currently contains about 100 million substances. That's 10 to the power 8, 1 followed by 8 zeros. That's a lot. It's growing at about 5 million substances a year. So if activity continued at this rate, more than 10 to the power 54 years of work by the entire world's laboratories would be needed just to explore drug-like chemical space. You can see the impossible mountain that chemical evolution, abiogenic evolution, has to climb. Conceptually, I think it's just, it isn't really, well, really what would be needed is a miracle in order for that to work. There's another problem as well, in that the base sequences of DNA actually resemble sentences in written languages, and they contain what's known as information. And information only originates in intelligent minds. How could information originate in the DNA by natural means? It's rather strong evidence that there was an intelligent mind behind the origin, behind the creation of DNA. And this is what's behind the growing popularity of the intelligent design movement. So there are good reasons to believe that a naturalistic origin for life isn't viable. You know, the naive optimism of pundits like Carl Sagan and Isaac Asimov from the last century, they wrote about a universe teeming with life, teeming with alien life. This is gradually giving way to reality. In fact, there's a whole bunch of books now where scientists are saying we're probably alone in the universe. Stephen Webb, for example, published a book called If the Universe is Teeming with Aliens, Where is Everybody? And Paul Davies wrote The Eerie Silence, Are We Alone in the Universe? The SETI program, he searched for extraterrestrial intelligence, has been searching for more than 50 years now without finding anything. And it's not the only one. There are actually dozens of search programs, not just searching radio frequencies, but also microwave frequencies. And they've been going on, as I say, for more than 50 years now without finding anything. That's one of the reasons behind the books that I talked about. You mentioned three well-known theories about the origin of life. The hydrothermal vents, was that the first one you mentioned?
Yes.
Yes. There are sulfide precipitates at these vents in the deep oceans. Sometimes they're called black smokers. And these sulfide precipitates show compartments, and they have catalytic properties. So there's been speculation that the compartments were the precursors of cell walls and membranes and could catalyze and concentrate organic compounds. The sulfides also provide an electrochemical gradient, and that was supposed to be the driving force for abiogenic synthesis. But there are problems. There's no explanation of how these inorganic compartments could transform into biological cell membranes. How could that happen at the bottom of the ocean? Virtually, the only organic molecule that's observed to be formed at vents is methane, and it's formed in minute quantities. Now, methane is a very long way from DNA or proteins, which are needed for viable life. Even if amino acids or bases were formed at vents, they'd be diluted and dispersed by the huge body of seawater. And then coupling them together to give protein or DNA is virtually impossible in water because it involves the elimination of water between the amino acids or base units. And this is particularly true at these boiling hot water at vents. This would actually split, that's hydrolyze any protein or DNA formed. So hydrothermal vents haven't found a great deal of favor amongst scientists. You mentioned tidal pools, I think. Was that the next one you mentioned?
Yeah, that's the second one.
Yeah. Well, that's the kind of equivalent of the primordial soup. If the whole sea was a tidal pool or the whole sea was a primordial soup. Components like amino acids or bases or sugars need to be concentrated, purified, and isolated if they're to react with each other and form proteins or DNA. But water hydrolyzes. It splits biopolymers like proteins and DNA. The coupling of amino acids into proteins requires the removal of water, as though it's strongly thermodynamically disfavored in water. Furthermore, in an ocean as saline as today, salt inhibits key prebiotic reactions. Again, a further problem for tidal pools. And I think in what I said about the immense ocean of molecules in chemical space, a tidal pool isn't going to be anywhere near big enough. What could accumulate in a tidal pool or even a prebiotic soup in the whole oceans is simply nowhere near what's needed for a random search for the components that are needed for the start of life.
So is this the most popular opinion how life originated in? Yeah.
Yes, you need dry conditions for them to couple into anything biologically useful. And then there's the problem of chirality, handedness. I'll come back to this a bit later when we're discussing one of the other one of the other things that you referred to. You know, experiments like the Miller-Urey one show the formation of simple organic components, but they get stuck there.
Yes, that's the next question. And can we just finish with a third opinion about panspermia?
Yes, indeed, yeah. Well, the panspermia hypothesis doesn't attempt to explain how life originated. It just shifts the origin of life to some other heavenly body. The advantage of this is that life only has to originate in a single location and not on every separate planet in the galaxy or every star system. The idea is that life would then be spread about via cometary or meteorite impact. Panspermia didn't get much scientific support. It deflects the need for an answer to explaining the start of life rather than doing it. It doesn't explain it at all. It's currently reckoned that life started locally on Earth, and nobody has come up with special conditions elsewhere in the universe that would make the origin of life more favorable than here on Earth. So I'd say very few people favor the panspermia hypothesis. Where would it originate? Where could there be somewhere more favorable than Earth? And there's still those problems that I talked about when I was talking about chemical space. And they're no more solvable anywhere else on the universe than they are anywhere else in the universe than they are here on Earth.
Yes, Professor Walton, but we found some amino acids or carbohydrates on meteorites or anything else. At least some claim so. Do you agree with that?
Yes, they definitely are found there. But there's a long way from amino acids, from simple organic compounds. I mean, nobody's ever discovered DNA or proteins on meteorites. And the problems start, I mean, those are simple organic compounds. They're comparatively easy to form. It's the coupling of those together to give proteins, to give DNA, to give carbohydrates, to give sugars. It's the coupling of those together, nothing that's really needed for the start of life is found. All the problems occur at the later stages. There are lots of other supposed things as well. You know, there's the polyaromatic hydrocarbon scenario. Polyaromatic hydrocarbons are also found in comets and meteorites, and it's been suggested that they might be the start of life. But polyaromatic hydrocarbons are very stable compounds. They're rather unreactive. How they would transfer into DNA or proteins or carbohydrates, even into heterocyclic bases, there's simply no explanation of how that could happen. Then there are clay surfaces. Again, how you get from a clay surface to a DNA, not explained. Radioactive beaches, again, not got very much leverage in terms of scientists. The very fact that there are so many different scenarios shows that none is really viable. I think there are about 20 or 30 different scenarios if you look in Wikipedia for the origin of life. The fact that there are so many shows that none of them is really viable, and there's no consensus amongst scientists about which one might be right.
Yes, interesting. And what do you think about contamination? Some say that maybe those amino acids or other stuffs are contaminated on meteorites or anything else. So is that possible?
Contaminated.
Yes.
Yes, you don't get them pure, which is what you need to make proteins out of them. I mean, one of the things that you find is this problem of chirality that I mentioned earlier on. You know, molecules have handedness. You know how your left hand is not identical to your right hand. You can't swap them over. and molecules are just the same. This is called stereoisomerism. So most molecules have stereoisomers, and nature only uses one of those stereoisomers. The amino acids, for example, all belong to the left-handed series of amino acids, whereas natural processes produce both of them mixed together. Now, if you start to make a protein from a mixture of amino acids, you get a protein that's inactive, that's biologically inactive. It's useless from the point of view of biology. Exactly the same is true of DNA. The nucleotides that go to make DNA actually have more than one stereoisomer. They have a whole bunch of stereoisomers, and only one of those is needed to make DNA. And if you form them naturally, they're very difficult to separate. There's no natural process that separates out just the one stereoisomer that's needed for real DNA, active DNA formation. So this is a huge problem for which there is no explanation from origin of life scientists, at least no viable explanation. Put it like that. You'll see scenarios out there, but they're not backed by experimental or factual basis.
But just quick question, Dr. Walton. Do you think that over time we will eventually explain the origin of life in a naturalistic way, or will scientists keep encountering deeper and unexpected complexities, realizing how much more intricate it truly is?
Yes, I do indeed think so. I think those very reasons that I mentioned at the start, the sheer huge numbers of possible DNA strands, the sheer vast numbers of possible proteins that can be formed from the basic amino acids means that a naturalistic way of finding just the few of amongst those vast numbers that are useful in terms of the start of life, it's an insoluble problem. It's a chemically insoluble problem. And that's why I think that some of these scientists are now writing these books saying that we're alone in the universe, and why intelligent design is gaining popularity continuously.
Yes, next question is about your really expertise, because what is the problem with oxygen and the early stages of the Earth? What challenge exists regarding the existence of the atmosphere that you discussed in the interview with Dr. Tim Standish? He was one of my guests on channel also, so from GRA, Geoscience Research Institute. So could you expand on that?
Yes, those type of experiments, the Miller-Urey type of experiments, whatever the atmosphere they use in them, they've confirmed that the presence of oxygen stops the formation of amino acids. It leads to oxidative degradation. Eventually, organic and biological things end up eventually as CO2. But oxygen is everywhere in our world. So was there oxygen in the Earth's original atmosphere? Most evolutionary scientists have to postulate that there was no oxygen in the Earth's original atmosphere, or that it was in a very low concentration, because of this degradation problem and the fact that you don't get Miller-Urey type experiments working. The problem with this is that oxygen is the most abundant element in the Earth's crust. And 46% of the Earth's crust is oxygen. Most rocks are oxides. So that's nearly 50% of the Earth's crust is oxygen. And it's overwhelmingly present, combined with hydrogen in water, in the oceans. So if we would have a solid crust where oxygen is a major component, a large liquid ocean, where oxygen is overpoweringly present, is it reasonable to conclude that that would be surrounded by an atmosphere with no or little oxygen in it? It seems most unreasonable to me. The presence of a large ocean also more or less guarantees there'd be significant oxygen in the atmosphere, because ultraviolet photolysis of water in the atmosphere releases oxygen. Direct observations from the moon during the Apollo 16 mission revealed substantial amounts of hydrogen were leaving the Earth's atmosphere due to photochemical dissociation of water. Jupiter's moons, Europa and Ganymede, they have surface water in the form of ice, and both are known to have atmospheres containing oxygen. The rings of Saturn, largely composed of ice, they also have their own oxygen atmosphere. It seems far more likely, whatever you believe, that the Earth's atmosphere has always contained substantial amounts of oxygen. Well, and a problem, suppose for a minute there was no oxygen in the Earth's atmosphere, then there'd be no ozone layer. So hard ultraviolet energy would reach Earth's surface, and hard ultraviolet energy degrades everything biological, dissociates them, even more quickly than the hydrolysis and so on that I've also mentioned. Could there ever have been a very little oxygen? Well, Origin of Life scientists claim that the widespread banded iron formations in Precambrian rocks, early Precambrian rocks, they have a lower oxidation state. Well, they have some iron in a lower oxidation state, and they claim that this shows that oxygen was very low level in the early atmosphere. But these banded iron formations are actually a mixture of a fully oxidized hematite and magnetite. And so overall, there are large amounts of these in Precambrian iron formations. So that would require an immense amount of oxygen for their formation from reduced iron. So by no means all geoscientists are happy with the idea that the banded iron formations show an early atmosphere that has a low oxygen concentration. You know, there are many reducing conditions in the Earth today. In the deep crust, in the mantle, in deep oceans, there's very little oxygen. So you don't need an atmosphere free of oxygen to explain the formation of the banded iron formations, to explain how they could have formed. They could have formed in these low oxygen situations that are already present on the Earth. Another thing that's often mentioned in this context is the mineral uraninite. That's uranium O2, UO2. Notice, though, it's still an oxide. Thermodynamically, UO2 is less stable than UO3, another oxide of uranium. But it only converts to UO3 in certain physical forms. There are physical forms of UO2 that are perfectly stable, and they can be transported as UO2. In fact, they're used as rods in reactors, in nuclear reactors, as UO2. So again, the presence of uraninite is by no means good evidence that there was a low oxygen atmosphere. You know, and if there were a reducing atmosphere, we'd expect the early Precambrian rocks to be very different. But in fact, they're not that much different from those today. And in fact, weathering, you know, if there were no oxygen in the atmosphere, weathering in particular would be very different. Today, weathering produces clays, which are complex oxides of silicon and aluminium. And clays are just as abundant in Precambrian sediments as they are today. So weathering, transportation, sedimentation appear to have taken place not very much different in Precambrian times from today. And those minerals containing reduced forms of iron and uranium, they can readily be accounted for in terms of local reducing conditions. So there doesn't appear to be any persuasive evidence that the atmosphere has ever differed substantially from its present composition. And no oxygen in the atmosphere, or little oxygen in the atmosphere, would have a dramatically inhibiting effect on the synthesis and accumulation of amino acids, for example, and any other organic components. It would virtually rule out the possibility that life arose in that way.
Okay, so many problems for naturalistic explanations. So, did you publish something on this topic? And what is the reaction of your colleagues? What do they say on this problem?
I did publish an article on it in a journal called Origins a long time ago now, but it's still available on the web. You can see it there. My colleagues, well, you know what happens to creation scientists. They simply get ignored. You know, my colleagues think, well, okay, maybe there are problems, but we're climbing Mount Improbable. Science will find a way. Science will find a way around these. It's just a matter of time, and the scientists will discover a way around. So they don't take it too seriously. Most of them ignore contrary evidence and go ahead in the hope that future science will solve all these problems. So I'd say that's the typical attitude. Either closing their eyes and ignoring, or saying, well, future science will deal with it.
Okay, thank you so much, Dr. Walton. And this is comment from my friend that he made on this topic, listening to you. So he says, evolutionists do not have to assume that the atmosphere was oxygen-free. Rather, this is unknown from banded iron formations, which indicate that ferrous iron accumulated in the oceans and was oxidized to ferric oxide with the appearance of cyanobacteria. This is confirmed by the fact that uranite and pyrite are not found after 2.5 billion years, as they are susceptible to oxidation, whereas before this period they existed in anaerobic environments where they remain stable. The same applies to rhenium and molybdenum, which are soluble in oxidative environments, and we see that after 2.4 billion years, their concentrations increase sharply in geological layers. So this is a longer comment. So what do you think?
Well, the banded iron formations I talked about them already. Even though there's a lot of more reduced iron in them, there's also fully oxidized iron, like oxides present in them. Not all geoscientists agree with I mean, that was a very favorable scenario that you did there. It's the kind of thing that you'll read in Wikipedia that your friend has given to you there. And the problems are those that I dealt with already. The uraninite, although it will convert to the more oxidized form of uranium trioxide, it depends very much on the physical form in which it is. And in certain physical forms, it will convert. In other physical forms, it doesn't convert. And in fact, it's transported quite readily as uranium-02 in certain physical forms. And then the other point to note is that there are lots of reducing conditions on the Earth today. In the mantle, some geoscientists believe that those banded iron formations arose not because they were formed under an anoxygenic atmosphere, but because they were uplifted from the reducing conditions that are deep in the Earth's crust and in the mantle. Others claim that they were deposited in deep oceans where there's very little water. So although the scenario that you talked about, that your friend mentions, sounds very plausible, there are alternative explanations for every single one of the points that he makes. And of course, the point that I made to begin with is that oxygen is the most abundant element in the surface of the earth, in the surface of the earth, and it's so abundant in water. How you've really got to get your head around the fact that around the idea that in a surface of the earth where oxygen is nearly 50%, and in a sea where oxygen is overwhelmingly abundant, combined with hydrogen as water, where photolysis of that produces oxygen, and it's known to be happening because the hydrogen from that process is escaping from the Earth's surface as observed from the moon. You've really got to get your head around that and still believe that there was no oxygen or very little oxygen in the Earth's original atmosphere. I mean, even the banded iron formations, I mean, the amount of oxygen that's present in them is enormous, really enormous.
Yes. Okay, and regarding what you said about creationists and their arguments being ignored, I spoke with Dr. Leonard Brand, also from GRA, and he said that it is not good when scientists ignore questions just because they come from believers, because they are maybe biased even, okay? He argues that it doesn't really matter where the questions come from if they are good ones. On the other hand, that is understandable because given that there are many fringe pseudoscientists among creationists, but on the other hand, not all creationists are like that, and they shouldn't be put in the same box. And their criticisms shouldn't be dismissed just because of someone professional. What do you think about all this?
Yeah, I have to agree completely. I mean, ideas should be evaluated on their merits rather than just throwing mud at the person who promotes the idea. But this is so often the tactic that's used by evolutionary scientists, trying to throw mud at their characters or otherwise discredit the person rather than dealing with the idea. And to me, it's a clear indication that their own arguments are weak, and because they have weak arguments, they have to resort to this mudslinging instead. And you see this on the web, in which creation scientists are routinely described as naive or stupid or bigots or liars. I mean, liars is another word that they use an awful lot. And these things are simply untrue in most of cases. And besides that, I mean, evolutionary science is just as likely to bias, in that the bias in that case is their materialist, secular materialist ideology or their atheist ideology, which is just as strong a bias for them as is religious, Christian, or whatever ideology for the creation scientists. So that's something to definitely watch out for. I mean, I mentioned already, watch out for reconstructions and artists' impressions, because this field of evolution is absolutely replete with misleading such things. And this is another thing that you brought up. If you find that the person is refuting creationist arguments simply by throwing mud at the proponent, then you draw your own conclusion from that.
Yes, I completely agree. I talked with a great mind, Dr. Dale Allison from Princeton University, and he is a historian, and he says something like this: I don't care if something comes from apologists or professors or majority opinion or minority. I don't care. I just follow arguments. So I think that's good thinking.
Yes, indeed, that's a proper attitude for true scientists to have.
Okay, Dr. Walton, can we wrap this interview and please can you say some conclusion, advice for people that want to study this topic that is really complex? And can you say how Bible helps you to be a better scientist?
Yes, that's quite an interesting but a big ask. Well, the first thing is don't be confused and don't be worried if you're in the minority. I forget who it was that said, 50 million people can be wrong. Somebody else said that the majority are almost always wrong when it comes to the most important questions in life. So you may be in a minority, but look for the truth. Don't look for the consensus, because the consensus could very well be wrong. That's one thing that I would say. It is a field that requires careful study. Don't rely on Wikipedia. I mean, don't trust Wikipedia when it comes to theology, when it comes to evolutionary science, when it comes to ideology of any kind. Then don't just Google and believe what Google tells you or what Wikipedia tells you, because you're almost certainly going to get naturalist, materialist, atheist ideology at the bottom of whatever's said. There are lots of valuable resources for the creation scientists now. The intelligent design movement, centered in Seattle, has a very good website which answers a lot of questions about intelligent design. There are good websites that you can look at. The Institute for Creation Research, ICR, answers a lot of these questions and refers you to the original literature that you can see. You, Nemanja, have mentioned the Geoscience Research Institute at Loma Linda University. They have a good site too, not as comprehensive as some others, but there's lots of good material there. Answers in Genesis is another one with a huge amount of material on it. Have a look at these. And then there's masses of creationist books as well, creationist literature. Don't just dismiss it because you've heard creationists are idiots or biased or whatever. Have a look at it. Have a look at some of the books by Jonathan Sarfati, for example. Read my books if you like. If you're interested in radiocarbon dating, have a look at my book. And hopefully my book, Justice for Genesis, will come out in a few months and you can read that. But there are lots and lots of other books as well. And those websites that I've mentioned will take you to them. I think all these things, you were saying too, all these things tend to confirm what we read in the Bible, in both the New and the Old Testament. There have been marvelous archaeological discoveries recently, which are illustrating and providing evidence that we can rely on what's there in the Old Testament, in the Genesis account itself. Wonderful, wonderful finds that have been coming out in the last decade or so. The Bible story is believable, creation is believable, it can be reconciled with science, and the Genesis creation account permeates the whole of Scripture. All four Gospels refer to Genesis. Jesus Christ himself, according to the Gospels, referred to things in Genesis. If the Gospels were wrong about Genesis, they were wrong about creation, then can we believe them about other things? But as I say, there's good evidence if you're willing to find it. There's very good evidence that the Old Testament and in particular Genesis can be reconciled with science rightly understood. And I'm one that goes along with that. I believe that, and hence I also believe the Gospels and the fact that the book of Revelation shows a situation where creation will be restored again. and where we'll live in harmony. Those that believe will live in harmony. Those that accept Jesus Christ will live in harmony in a world made new again, in which Eden is restored and re-beautified. And I'm looking forward to that day.
Dr. Walton, thank you very much. This was inspiring and it was a pleasure to listen to you. And I really honestly say that. So I really enjoyed learning from you today. Dear audience, if you enjoyed this interview, don't forget to like this video, leave a comment with your thoughts or questions, and of course, subscribe to NT Podcast for more discussions like this. If you would like to support our work, you can do so through donations, and the links are in the video descriptions. Thank you for your support and see you in the next episode. Thank you.
Thank you and goodbye.